Hello, everyone. This is the lecture for section 5.1, approximating areas. So chapter 5 is going to be, so we're done with derivatives now for a little while, okay? We're now going to move into another portion of calculus, which is called the integral, okay? This is what the bulk of Calc 2 is going to cover. We're going to just get started with it, do a couple rules here and there, and then you guys are going to pick more of this up in Calc 2 once you get there. Okay. We will need derivatives, but not as much as the previous couple chapters, right? Okay, so the first thing I want to do is start by giving a very, very, very crude definition of what an integral is, specifically what we're going to be carrying out for the end of this class and for, like I said, the bulk of calculus 2 is sort of figuring out what a definite integral is, okay? And that is defined to be the area under a curve, okay? And it's denoted by this thing. So you guys already see the little squiggle from the integral, from the antiderivative that we were playing with in section 4.10, okay? So if we have, I'm gonna draw my X and Y here, right? Here's my X and here's my Y, here's my X, right? And let's say we had a curve, right? So let's say this is f of X, right? Then there's going to be an A and a B, right? An A and a B. Make that a little more legible, right? B, right? So the A is going to be dot, 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 dot. The B is going to be that. So what the integral does is basically gives us how much this area is right here. The area underneath that curve. Okay, that is what the integral is. Okay, it's at least this is what we're going to be doing with the integral, right? We're going to be sort of delving into some basic concepts and the understandings of a definite integral, maybe get into some physical applications, right? And leave the more complicated stuff, like I said, for Calc 2, okay? The one thing we will need in order to figure these things out is the idea of the area of a rectangle. And that this is the primary way we're going to be sort of developing our idea for an integral, okay? The way that we find these integrals, how we're going to define them, at least at the very beginning, is that we're going to have some box that's over two specific values like this, right? So actually I should draw them solid. Okay, and that box, in particular this one, right? This one is represented by some f of xi value, right? It's got to go some amount high, right? And it's going to be defined by some value xi, right? And the idea, right, is that the area of this, right? So the area of this is f of xi, right? Let me not call that, well, yeah, that's going to be an xi. But it's going to be, there's a sort of a width here, a delta x, right? The area of this little box is given by that, right? It's the length times the height. That's simple, right? And if we do this over and over and over again, underneath the curve, we'll get a nice representation for our area, okay? So that's the only big thing I think we're going to need, is that the area of a rectangle is just length times its width, right? Or it's length times its height in this case, right? Okay. Much of this section is really notation and getting the notation right and developing it off of the notation. Again, like I've been mentioning throughout the class, I like pictures because the pictures makes much more sense, or at least puts the definition that we're doing into some context, right? Okay. So let's go ahead and get started. Okay. The first thing I want to define is the definition of a partition. Okay. And that of a regular partition. Okay. So let A let I be an interval from A to B somewhere, okay? So let me scroll up. I'm gonna go ahead and it's not gonna be as big as what you guys usually would remember me doing. So this is an x-axis and this is a y-axis. I'm not going to draw a graph here. I'm just going to be defining a partition and a regular partition in this case. Okay, let me read it out first. A set of points P, and it's going to be a collection of points of xi, right? And the I is sort of like an index, with A being the first one, B being the last one, and then a bunch of points in between. Okay, and that divides up my interval I into sub-intervals from x0 to x1, x1, x2, x2, x3, x3, x4, so on and so forth. Anything that divides up your strip from A to B into smaller little intervals, that is what we call a partition. Okay, so then let me go ahead and start with, so let's say this is my A, right? And this is my B, okay? And let's say I start dividing this up. Let's say this gets divvied up, right? So, uh, uh, uh. This is all I'm doing. So this is going to be my x0. Sorry, this is going to be, well, A is going to be my x0, x1, x2, x3, x4, dot, 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 right? Until the very end. And this one's going to be x little n, okay? Anything that does this for an interval AB is called a partition of the interval AB, okay? If the partition divides I, your AB, right, your interval AB, into subintervals of the same width, the width being this right here, B minus A divided by N, then that is called a regular partition. So that means every single one of these chunks, this one, this one, this one, this one, this one, so on and so forth, right? If all of those are exactly the same width, then that is called a regular partition. So you can chop up the interval A to B however you want, right? So some pieces can be bigger, some pieces can be smaller, right? But if you do it where each piece is the same size, then you have a regular partition, okay? So that means every one of these, right, including this one, all of these, right? If all of these are delta x, right, which is defined to be B minus A over N, if all of these partitions right here are this big, B minus A divided by N, then you have a regular partition. Okay? Okay. The next two definitions are, they sound complicated. Oh, excuse me. The next two definitions sound complicated, but they're really not. Like I said, I like pictures. The pictures make the explanation much more clear, okay? So the first one that I'm going to do is that of a left endpoint approximation, okay? So let me read it out first. I'm going to read the other one out too, the right endpoint approximation, okay? So on each subinterval xi minus 1 xi, so on each chunk, right, that's produced from the partition P, we're going to construct a rectangle with the width delta x and the height equal to xi minus 1. So look at what it is, right? So I'm referring to this endpoint right here, okay? Then the area of that rectangle is going to be given as that, okay? Adding all these areas up gets us what we call an approximation for the area under the curve A. And we're going to call that L sub n for a function. So for the left endpoint approximation with n divisions, right? So now let's get to the right endpoint. So on the right endpoint, right, we have the same start on each subinterval xi minus 1 comma xi from the partition P, right? We're going to construct a rectangle, right, with the width delta x, so the same width, but in this case, the height is xi. It's going to be the right end of the interval that you just created, okay? So that's what's giving us our right endpoint approximation, right? Then the area of all these rectangles is equal to this right here, right? So this is going to be the height, and this is going to be the width, right? And if we add all these rectangles up, this is going to be an approximation to the curve under A. Or sorry, the curve, the area under the curve. We're going to call it A, okay? And to introduce, whoops, look at me go. That's supposed to say right. Typo. Okay, we're going to use this notation just as we did with the left endpoint. This is going to be the right endpoint approximation for our function. Okay, so let me get into what these actually mean. Okay, and what I'm going to do is, as you guys can see, there's formulas down below that we're going to sort of, that'll sum up everything that we need to do here. Okay, so the left endpoint approximation. So let me go ahead and draw my X and Y graph, right? Here's my X, here's my Y, and here's my function. Let me make it a little less pronounced, maybe a little higher. There we go, I like that. Okay, here's our function, right? For the left endpoint approximation, right? Let's say we had, I'm going to use the same colors that I was using before. Here's my A and here's my B, right? I'm going to choose out an xi minus 1 and an xi, right? So that means that I have a box like this. Right? And notice it's specifically, I'm using the left end of my box, the left end of the subinterval from my partition. So this point right here, right, is f of xi minus 1, right? And I said this is a regular partition, right? Let me make this a little smaller here. X sub I minus 1, right? I know that this is a delta x, right? Where delta x, let me write it over here, is given by b minus a divided by n, right? So we know that this is a fixed amount, right? The area for this little box right here, area, right, is going to be f of xi minus 1, right? That's the height of my box, times my delta x, the width of how big it is. Okay. So that is the area of this rectangle right here. And the idea now, right, is that we do this for every single little subinterval, right, for my partition AB. So then that means that there's going to be a next box over, right? And there's going to be a next box over that way. All of them, there we go, right? All of them are being, let me do one more, right? There we go. All of them are being dictated. So notice here's one interval, right? I used the left endpoint of this partition down here. For this next box, it's the left endpoint of that box. For this rectangle, it's the left endpoint of this box right here. So on and so forth, right? So I just did the area for one rectangle, right? What we would do is we'd do this same operation for all of the rectangles, right? For all of the partitions in for all the subintervals from my partition, right? And then add them all up. Okay. That's what this big, huge, nasty equation means right here. And that's sort of like the shorthand for this one right here. So notice what happens here, right? Notice that if we start this process, right, then f of x naught, so the very first box that's going to be over the value a here, right? That's going to be a, right? And it's going to be the next box over, the next box over, right? And it's going to end at n minus 1. So the one right before b. So let me draw that in. Whoa, wrong color. I'm going to extend this all the way over to, right? So then this right here is supposed to be xn, right? That's supposed to be the end of my partition. But notice we end right before it because since we're doing left endpoint, that one's the one that counts. The one on the left of that box is the one that counts. Okay. If we want to do the right end approximation, it is the exact same argument, with the exception of we're using now the right endpoint of each one of the subintervals from our partition. So let me go ahead and draw that out to be sort of clear about it. I'm going to draw my x-axis and my y-axis. Okay, and here's my function. I started it around here and I went like this, right? Make it a little bit more there. Yeah, I'll take it. I'll take it. Nah, I'm gonna do it one more time. There we go. Okay. So again, I'm going to start off A to B, right? So here's A and here's B. Okay. I'm going to go ahead and choose a subinterval inside. I'm going to use the same notation from the definition. Let me actually make this a little bigger. Xi minus 1, Xi. So then this thing has a box. It has a rectangle right above it. Right. Notice how I drew it. It's now dependent on this value right over here. On the right-hand side of that subinterval. Okay. So then this means that this height right here is f of xi. This right here, same idea. This is going to be a delta x. They're all the same width, right? So and therefore the area here is going to be, right, A is equal to f of xi times delta x. That's where I'm getting my formulas from up above, right? Okay. And again, the idea here now is we are going to create multiple boxes, right? But they're all going to be defined. Whoa. They're all going to be defined by the right endpoint. You guys hopefully see how I'm drawing this out. They're all defined by the right end of that subinterval. You see that? So for example, to clarify, right, this box is defined now by this end of this subinterval right here. Okay. This box is defined by this end of this subinterval. Does that make sense? Okay. So now notice in this one, right, here's the nasty drawn out equation, right? And here's the shorthand. Okay. Notice how this one starts. X sub 0 is supposed to be our value A, correct? Right? But this one starts at f of x1. because if x naught is supposed to be our very first value, which is supposed to be a, right? And we're doing the right end approximation, right? Then that one's the one that doesn't count. This end, for the very first box, this end is the one that gets all the attention. That makes sense? And then likewise, right? As we go toward the end, as we move over to b, right? That is x to the n, and that is going to be the right end of the subinterval from our partition. So that's why we end there. Okay, that's it. That is the difference between the left end and the right end approximation. Same argument for both, right? But we sort of give more attention to one end over the other, depending on which one we want to do. If we want to do right end or left end approximation, okay? Simple enough, right? Okay. How does this all work out? So that's what I want to do next. I want to do an example to show you guys how this sort of works out, okay? So what I'm going to do here is I'm going to do the left end approximation, okay? The left end approximation for this curve right here, between 0 and 2 with n equal 4, okay? So then that means we are looking for this area right here. Here's 0 over here. Here's 2 over here. So I'm going to draw a line that goes straight down from here. Straight down, I said. Much better. Here and here, right? So we are looking for this area right here. Right? We're at least going to approximate this area right here. Right here. All of this. This is what we're looking for. Okay? And we're going to try to do it using left end approximation. Okay? So the first thing I'm going to do, right, is I'm going to find out what my delta x is going to be. I need to find out how big each one of my boxes is going to be, okay? And that's going to be always b minus a divided by n, right? We know what b and a are. That's over here. So this is my a and that's my b. So it's going to be 2 minus 0 over n, which is now 4. 2 over 4, 1/2, right? And I'm just going to go ahead and put 0.5. We know that our partitions are going to be 0.5 big, right? That means my first partition, thankfully my graph is already set up this way. My first partition is going to be up to 0.5. The next one is going to be 0.1, or sorry, 1. The next one after that is going to be 1.5. And then the last one should be 2. That's going to be the last sort of tick mark, right? So we have our boxes, okay? Now we're going to go ahead and do the left end approximation, okay? I'm going to go ahead drawing my boxes, okay? Here's the first box. Notice how it only goes as high as whatever 0 is because I'm using the left, right? The next one at 0.5, the graph goes this high. So I'm going to go that high. Okay, the next point goes that high, right? And then the last one goes that high. Okay, so here are my boxes using the left end approximation. So notice, let me circle the ends that matter here, okay? Since this is left end point, right? I need the left end of this box. So it's going to be 0, left end of this box, 0.5, left end of this box, 1, left end of this box, 1.5, and that's it. Those are our 4 boxes, right? Okay. So now I need to find the area of each one of these, right? So what I'm going to do now is I'm going to go ahead and use this formula that I have up here. So it's f of x0, f of x1, f of x2, f of x3 times delta x by each one, right? So I'm going to come right here. So my area here, right? My area is going to be f of 0 times delta x, right? Plus f of uh, 0.5 times delta x, right? Plus f of 1 times delta x. Those are deltas. It's hard to draw triangles. There we go. Plus f of 1.5 times delta x, okay? So let me go ahead and color code these really quick. So this right here, right, is going to be sort of like the calculations for the area for this box right here, just this very first one. Does that make sense? This calculation right here is the area for just this box right here, right? This one right here is going to be the calculation for just this third box right there, okay? And then lastly, right, this right here is the calculation for this box right here, okay? That's it. So at this point, at this point, we can go ahead and plug these values in. So we can find the explanation for, or find the value for this, the value for this, the value for this, and the value for this. And you can go ahead, plug it into this thing, and it'll give you a number. That's perfectly fine. Again, that's a lot of arithmetic that I really do not have. Nobody's got time for that. So what I'm going to do instead is I'm going to use Desmos. I'm going to show you guys how to actually, what I'm going to do is I'm going to show you guys how to actually use Desmos to calculate these values for you, okay? Assuming you can plug in everything in the calculator correctly, of course, okay? So we're going to start off with a blank version of Desmos, okay? I'm first going to plug in my function. So this is going to be f of x equal 1/2 x squared, right, plus 1. So let's go ahead and zoom into the thing that we really want. We want this right here. And I think I'm going to change this so that the x goes just up to 3. There we go. I'm going to make it a little bit more. So this is the graph that we have over here. You guys see that? Cool. Okay. So it's got all the bits and pieces that we need, right? But now what I'm going to do is I'm going to use this to find these values, okay? So in the second box down, I'm going to go ahead and hit this plus that's right here, and I'm going to go to table. And it's going to give me an x1, y1, okay? I'm going to change the y1 to f of x underscore 1. So what this is going to do is if I put something in the left-hand side of this table, it'll pop out the function value at the right hand, on the right-hand side of the table. Does that make sense? And it'll put a point down on the graph to show you what you're actually computing. Does that make sense? So I'm going to go ahead, put in f of x0. So that means 0 is in for my x. It's going to give me 1. That's cool. Okay. The next one is supposed to be 0.5. So I'm going to put in 0.5. And it gives me my function value there. Okay. The next one is 1. And the one after that is 1.5. So it's giving me my function values here. Okay. Now, to make the calculations a little neater here, notice that in this entire expression that I have written out right here, right, all of them have a delta x multiplied to them. So I can actually do delta x, I can factor out delta x, and I can just do f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. You guys see how much neater that makes it look? Okay. So then delta x, actually, let's go ahead and just compute these out. We know what f of 0, f of 0.5, f of 1, f of 1.5 is. It's these values over here. So I'm going to just use this over here. I'm going to do 1 plus 1.125 plus 1.5 plus 2.125. And that gives me 5.75. So then this right here is 5.75. Okay. And my delta x, we know that is 0.5 because we calculated it earlier. So this is going to be 0.5 times 5.75, right? So then I'm going to grab this next spot right here, 5.75 times 0.5, and that gets me 2.875. Okay. Let me go ahead and come back to here. So this right here, the 2.875, this is an approximation using these areas right here, up to here. Right? Now, notice, right? This is a very, very crude approximation of the area under this curve, right? And the reason why is because there's all of this that's not being taken into account. We were only using the areas of the boxes from right below it, right? And then there's a little smidge of it right there. You guys see that? So this is a very crude approximation to the area under the curve. Okay, it's something, but it's not entirely close, really. Okay, so this is how you do the left end approximation. If I were to ask you to do the right end approximation, you'd just basically be switching these points right here. Instead of using the left-hand sides of each one of these boxes, you'd be using the right-hand side. So this end, this end, this end, and this end. Notice that this one, I'm not highlighting the one at x equals 0 because that's not the right end of the interval. Okay. Okay. So at this point, what's going to come up now is a quick check. Okay. For the odds, I want you guys to do n equal 8 for this function using the left end approximation. Okay. And then for the evens, I want you to do the same thing for the same function over the same interval with 8 partitions, but you are using the right end approximation. Okay. So both of you, both of the end odds and the evens are doing the exact same area. Okay. But one's doing it with the right end, one's doing it with the left end. Okay. Okay. So what I want to move on to now, right, is a little bit more of the definition for. We're getting closer and closer to the bona fide definition of an integral, of a definite integral. Okay. So like I said above, right, depending on whether you use the left end or the right end approximation, right, you're gonna either get an overestimation, right, because your boxes are gonna sort of take up area that isn't under the curve, right, or you're gonna get an underestimation, right, where your boxes, just like we had in the example above, the underestimation was because our boxes never hit like the very top of the graph, right? There's always that little bit in green that I was highlighting that we never counted. Make sense? Okay. So this is how we're going to be we're going to be getting rid of that idea of an over or underestimation. Okay. So let me first start by defining what a Riemann sum is. We've already done it, actually. Okay. So let f of x be defined on a closed partition AB, and let p of x be any regular partition. So the delta x's are the same, right? Then for each I, let xi be any point within the subinterval xi minus 1, comma xi, okay? Then the Riemannian sum is defined for f of x by this function right here, okay? So let me explain what this means. It's not anything different from the left endpoint and the right endpoint approximation, right? But this is now a much more general sort of definition of those areas, okay? So here's my x and here's my y, okay? So here's my a to b. I'm going to draw in my a and my b, right? And I have a function, right? Make it a little higher up. There we go. Okay, here's my function, okay? I know I can divide this up into partitions, and I'm going to take one in particular, right? This is going to be my xi minus 1, and this is going to be my xi, okay? And we know that there's a box above this, right? The Riemannian sum, right, is defined by this thing right here. Before, in the examples I was doing before, and in the definition of left endpoint and right endpoint approximation, we were specifically using the left endpoint or the right endpoint of our subintervals, right? Okay. The actual definition for the Riemannian sum, it doesn't matter what point, either what point you use for your box, so long as you pick out a representative point from somewhere in that interval. That's what it's talking about. That's what this definition is for a Riemannian interval or Riemannian sum. So instead of picking the left or end, I just pick any point I dang well choose between these 2 points. So I can pick this point to be my xi, right? This thing has a box, but this box now goes up as high as xi does, f of xi. So that's my apologies. So actually, let me get rid of that. I'm going to box this up right here. Here's my representative value. So it goes up by whatever that point is. So this is my f, and I messed up already. Not much, but enough to confuse you maybe. xi is that point. So this right here is xi star. The xi star is sort of like a representative value within each subinterval. Okay, so that means this point up here, the height of this box is going to be xi star. Whoa. Which makes the area of this box f of xi star times delta x. Okay. Same idea as before. We grab all of these boxes over all of the subintervals and we add them up. That is going to be the definition for our Riemannian sum. Okay. Okay. So now what I want to do is take this idea a little further. So from the last example that we saw, right? This is only good for estimations. Okay, let me actually scroll back up here. Because now, if you guys notice, let me take this. There's this little bit that's not under the curve, this little bit of green that's right there, right? That's being added with this area, right? But it's not under the curve. But then there's this big other piece right here that's not counted either, right? So it's sort of like a give and take, right? So how do we remedy that? That's where we have to do this idea of a limit, okay? So essentially saying, let me actually scroll back up here a little bit. There we go. Essentially saying what we can do, right, is what if we make these little subintervals right here, what if we make those smaller and smaller and smaller and smaller, right? That means our delta x is getting smaller and smaller and smaller, right? Which means there's less of this going on. There's less of little pieces getting left out and the other pieces getting left out here. Does that make sense? There's less and less of that happening. If we make our delta x, the width of each one of those boxes, smaller and smaller and smaller and smaller, right? This is the idea of a limit, right? From chapter 2. Okay, so then that's the next definition. Okay, that let's say you had an f of x to be a continuous non-negative function. For now, we're going to play around with non-negative, so it has to, your whole function has to be positive. Okay, on an interval a b, and we're going to let this thing be one of those Riemannian sums from above. Okay, then the area under the curve is given by this equation right here. Okay, notice that this is no different, and I'm missing a star on this one right here. Okay, notice that this definition is no different than the one above for the Riemannian sum. The only difference here, though, it's more like an addition, right, is this thing right here. There's a limit as n approaches infinity. Okay, so notice that the n, right, it's the same n from our delta x, right? So what we're doing here, right, is the b minus a, right, my interval is still going to be the same length. It's going to be a b and an a. But the n is getting infinitely bigger, aka, in this case, this thing is getting infinitely bigger. So instead of doing n equal 4, we're doing n equal 8, n equal 10, n equal 50, n equal 100, n equal 1000, okay? And if you remember what delta x did, right, it was the width for each one of those subintervals, and the n was the number of sort of partitions, the number of cuts we were going to sort of divvy up a to b in, right? So what this is doing, right, is making each one of those subintervals smaller and smaller and smaller. So that's the idea of taking the limit as n approaches infinity, okay? And as the width gets infinitely smaller, right, due to the division by n, we have less and less of an overestimation and underestimation, right, as we keep making that n bigger and bigger, right? And that produces a much more accurate measurement of the area under the curve of f of x. Okay, so what that means is our left endpoints, right? If we use our left endpoint and right endpoint approximations, if we can see that the left endpoint approximation and the right endpoint approximation, they're going to have less and less of an over underestimation, right, as that n gets bigger, right? Until both of those limits start to equal each other. So what does that mean? So let me go ahead and do sort of like a picture here, right? So let's say we wanted, you know, big box to start with, right? So let's go ahead and use this as my left-hand approximation, right? And then I'm going to make the the delta x smaller, right? So instead of maybe that one box, I'm going to do the same curve, pretend it's the same curve, right? So same box, but I'm going to divide it up into smaller boxes, right? So now this is there, this is there, this is there. You guys see what's happening, right? This over approximation is much smaller now, right? And then I'm going to do it again, right? So same graph. I'm trying, right? But now the boxes are really small, right? So notice how little the over approximation is now, right? And we'll do this over and over and over again, right? As n approaches infinity until we get, whoa, until we get something, right? Here's my curve. Until we get from A to B, right? We get this area right here. We get a much finer and much finer approximation for this area right here, right? Got it? This was going to be for the left end, right? And if we do the same thing for the right end approximation, right? So I'm going to do the same little squiggle, right? Whoa. So right end approximation this time, right? We're going to use, pretend it's the same squiggle. Please pretend it's the same squiggle. I'm trying, right? That one, this box, has a massive underestimation, right? Because all of that's not there, right? But then what we do, right, is we make those partitions smaller. So here's the squiggle there, right? So we make those partitions smaller now. So that point, let me do one more in here. That point, right? So this is one approximation. This is another. This is another. This is another. So notice the under approximation that we had in the first one is now much less. It's been decreased by a lot, right? We do it again. We make the partitions even smaller. Whoa. Right? So same squiggle, pretend it's the same squiggle, right? And we're making the partitions even smaller now. So this is now really tiny, like even smaller, right? And again, using the right end approximation. So that, right? Notice that the error, right? The over or under approximation here is now much smaller still, right? We continue doing this, right? Over and over and over again as n approaches infinity until, a little bigger, there we go. Right, so keep in mind, we want to find this, right? I'm gonna find this area right here. Pretend they're the same area, please. I'm trying to draw it freehand, and it's hard. There we go. Okay. So this was doing it using the right-hand approximation, right? So at the very end, right, we have two different expressions here. There's going to be a left-hand approximation here. So this is going to be my whoops, got them backwards. This is going to be my left-hand approximation, right? And this is going to be my right-hand approximation, right? Okay. These are going to have an overestimation and underestimation because of the endpoints that we use for each subinterval, correct? Okay. But since we're making those n's, since we're making that n infinitely big, that means we're making the partitions infinitely small, right? Which means that those over and underestimations become very, very, very tiny. Okay, to the point, right, where, and this is the portion in calculus, or at least in math, I'm going to do a bunch of hand wavy stuff. What's going to end up happening is that those over and underestimations become negligible. And we can essentially say that both of these approximations are now essentially equal. That our left end approximations and our right end approximations essentially are equal plus or minus a very, 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 very small underestimation. Okay. That's the idea of a limit. All of this can happen only if, right, we do that n approaches infinity. Okay. A lot of this is a bunch of sort of like a thought process or a thought experiment for everybody. Okay. Uh, there's very little, I would want to say there's very little math. There's a whole lot of abstract thought here. Okay. So if you need to really listen to this again, please do so. Okay. At least if you want to pick up the theory on it. Okay. And I believe that is it for this section. So if you guys have any questions on the material, I've got my drop-in Zoom hours from 3 to 6 o'clock every day, about Monday through Thursday. Come on out, come on down. Or you can send me an email or send me something to the discussion. Any which way you can get a hold of me, that'd be great. Okay. Besides that, study up, and I'll see you guys around.